Right, so today we're going to be looking at how we write half equations. And these half equations are in the context of metal reactions. So currently, we are studying the reactions of metals. We have just in our books written a reactivity series of metals. And now we're going to be looking at this new skill of half equations, which is looking at how individual metals react in a reaction, in whether they lose or gain electrons. So that's the idea of this. So I'm going to tell you what a half equation is. Half equations tell the story of a reactant. Tell the story of is a bit like poetic, isn't it? They tell the story of a reactant rather than like two reactants in terms of electrons Okay. So you might not know what that means yet, and that's not really the point. By the end of the lesson, you'll know what that means. So they're going to tell the story of a reactant in terms of electrons. So when a lot of chemicals react, a lot of chemical reactions involve the movement of electrons. Not all chemical reactions, but a lot of them do. So in some chemical reactions, chemicals lose electrons and something else will gain electrons. So I'm going to introduce this idea, or reintroduce it to some of you. Oil rig. Okay. So some chemical reactions involve movement of electrons. In fact, an awful lot of them do. Oil rig is a really, really useful mnemonic that tells us that oxidation is loss of electrons. That's the OIL. Oxidation is loss. And we talked about loss of electrons before. We said when group 1 metals react, they lose electrons. We know, actually, from our previous lesson that when any metal reacts, it loses electrons. Oxidation is loss of electrons, and reduction is gain of electrons. So the skill we're going to be looking at today is we're going to start off by writing overall reactions. Traditional equations, things like magnesium plus hydrochloric acid makes magnesium chloride plus hydrogen. And then we're going to look to see if anything's losing or gaining electrons in those equations. In fact, the types of examples we're going to start off with are going to be fairly straightforward. They're going to be displacement reactions. All right, so we're going to look at half equations in terms of displacement reactions. So that's where we're going to start. Because it's sort of where we ended the last lesson. Displacement reactions always involve oxidation and reduction. At A level, there's a nice little word we use for oxidation and reduction reactions. We call them redox reactions. You see why? Reduction, oxidation. Reduction, oxidation. Not redox, that's all about. And if you're watching this video back, everybody's laughing. Right, so displacement reactions, always involve oxidation and reduction. So what I'm trying to say to you is, just getting this clear in your head, there's loads of chemical reactions out there. Loads. Some of them don't involve movement of electrons. Some chemical reactions don't. They just involve, they don't involve electrons at all, particularly. And there's an awful lot of chemical reactions out there that do involve movement of electrons. So something loses an electron, something else gains it. And they are called redox reactions. So we're going to be looking at some of these redox reactions. Now, that's an A-level term, but we're going to look at reactions where something loses electrons and something else gains. And the type of reaction we're going to start off with, it's a nice introduction, is displacement reactions. So I'm going to start off with a word equation for a displacement reaction. Now, in the last lesson, we said that displacement reactions are when a more reactive metal displaces a less reactive metal from its compound. So I'm just going to write one that definitely works. I'm going to go with magnesium plus calcium chloride. So in this, I could look at my reactivity series, which I haven't got in front of me, which is a shame, but I know that magnesium is more reactive than calcium. No, what a bad move. I totally got that the wrong way around. If you're watching this back, that was a deliberate mistake. What we would write here is no reaction. Yay, cool. But I just absolutely messed that up. Calcium is more reactive than magnesium. You might be able to tell I didn't plan this and I am winging it. So let's go again. Let's go with calcium chloride. Calcium, sorry, plus, I'll get there, magnesium chloride. That was it. Pretty fundamental error straight away there. All right. Calcium is more reactive than magnesium. All right, so we've got magnesium chloride. We drew a little picture last time, or there's magnesium and chloride having a lovely time. Calcium turns up. I'm stronger, or whatever it might be. And then calcium and chloride pair up, leaving magnesium on their own. That's the idea. Okay, so we're going to make calcium chloride plus magnesium. Over the years, I've started to have a bit of an issue with the pairing up of people because it doesn't really work that well, and it's a little bit, I don't know, it's a bit old. It feels a bit old-fashioned. I prefer chloride as a football. All right. Here is a year 7 student with a football. All right. And calcium is a year 8 student who says, "Give me your football." I think it just removes any sort of weirdness around it. It's just straightforward bullying. All right. Because bullies always win, right? And what you end up with, because calcium is a bigger boy, it's a bigger girl, she did my football. All right, there's calcium chloride and there's magnesium chloride. All right, so in the world of chemistry, the more reactive metal always gets, in this case, it looks like they get the football. It looks like it's a story about the football, the chloride. But if we write this now as a full symbol equation, so this is a word equation, which I would expect you to be able to do lower down the school. Calcium is Ca. Magnesium chloride, anybody in the class know that one? So we've got a lot of people with MgCl, which is a good start, but it's knowing that it's MgCl2 is very advanced. Magnesium's group 2, chloride ions are Cl minus. Don't worry if that's not the aim of today to know that. We're going to make calcium chloride, CaCl2, and we're going to make magnesium Mg. Now, this is a symbol equation. And of course, a lot of you will still be like, oh, I've never been that good at knowing why the formula is CaCl2. It's to do with ion charges. There's a symbol equation. All right. What we can do here with a full symbol equation like this is we can get rid of any spectator ions. All right, so calcium is just calcium. It's not an ion. Magnesium chloride is made up of Mg2 plus and 2 Cl minuses. I'm just expanding this out. Calcium chloride is an ionic compound. It is made of calcium 2 plus and 2 Cl minuses. And magnesium is just Mg. So when we look at this, this is any of the ionic compounds, the MgCl2 or the ClCl2, I've looked at what ions it was made of. And if you look at that now, you can see from left side to right side, there is one thing that has not changed between the two sides. What is it? Yeah, it's the chloride. The calcium has become calcium 2+. Something has happened to that. The calcium has definitely changed. The magnesium was Mg2+, it's now Mg. That has definitely changed. But the Cl-, the football, is just a football. It was a football before, and it's a football after. It's what's known as a spectator ion. The football is actually irrelevant in this story. What is relevant is a year 8 child bullied a year 7 child. A more reactive metal made a less reactive metal cry. All right? And that's what we're looking at here. The football is still a football in the end. It's what we know in chemistry as a spectator ion. Anything that's just getting passed around is not important. So if we remove the spectator ion, the story of what's going on becomes more interesting. It becomes more obvious. We end up with calcium plus Mg2+, makes calcium 2+ plus Mg. To make this relatable for your GCSEs, this type of equation here is called an ionic equation. Remember, today we're looking at half equations. That's an ionic equation, and we have removed spectator ions. All right. So I'm going to just turn over the page now and rewrite this equation out. All right. So, in this equation, we had calcium Ca meets Mg2+. I've got rid of the football now because it's not really about this. The calcium becomes Ca2+, and the magnesium becomes Mg. This is my ionic equation that I've just written out again, nice and neat. All right. So what we're going to do, and what you could be asked at GCSE, is you could be asked to write half equations for this. Now, the first sentence I said about a half equation is the story of one of the elements in terms of its electrons. So I'm going to use some arrows here to visualize what we're about to do with half equations. This is an overall ionic equation. The half equation, one half equation is going to tell me the story of calcium. And another half equation is going to tell me the story of magnesium. Hopefully you can see why they're called half equations. We've got an overall equation, we're going to split it into two halves. Is that all right? That was all part of the setup. So, in a displacement reaction, one of the metals goes from being a metal to being a 2+, and the other metal goes from being a 2+ to becoming the metal. So these are two individual stories we can tell by writing half equations. So, I'm going to write these two half equations now. First one, I'm going to tell the story of calcium. In this equation, calcium becomes calcium 2+. And in the other half equation, magnesium 2+ becomes Mg. All right. So, we are finally at the point where we can balance these half equations. And this is the story of electrons. I want to know what has happened when calcium becomes calcium 2+ in terms of electrons. How does calcium become a calcium 2+? People in the room, you can discuss that now with your neighbours. Are you sure? Have an argument.
It's lost to electrons.
It's lost to electrons. So, for a calcium to become calcium 2+, the consensus seems to be that a calcium needs to have lost 2 electrons. Now, I'm going to write some electron configurations under here to remind us of how this works. But I want to remind you that an electron is an E-, it's a negative charge. Calcium is 2882. When calcium reacts, it loses 2 electrons and becomes 288. To become a positive ion, you have to lose 2 electrons. Now then, how do we draw that? Now, I'm going to go onto a separate piece of paper to show you the 2 options. You don't need to do anything right now. So we've got calcium becomes calcium 2 plus. You might want to write it like this at first. Calcium losing 2 electrons. You might go calcium losing 2 electrons. Calcium minus 2 electrons. I don't like that. GCSE doesn't like that. AQA doesn't like that. But you might see it in textbooks. It's just telling a story. Calcium loses 2 electrons. If you lose 2 electrons, you become calcium 2 plus. Is that alright? Now, that is one version, but I don't like it. The version we're going to do, actually, I'm going to go back to the book, and this is the one I want you to write. Calcium becomes calcium 2 plus, plus 2 electrons. What this is saying is, here's a calcium with 2 plus, this is me with my 2 electrons, and then at the end of this, I'm going to lose my 2 electrons. You're going to drop them down there, and now it's me and my 2 electrons that I've lost. So that's how we're going to describe it. This equation balances really nicely now. If you notice on the left-hand side, there is no overall charge. And on the right-hand side, there's no overall charge because I've got 2 pluses and 2 minuses. It balances out. This is calcium losing electrons. This is oxidation. Because oxidation is loss. It will make more sense in a minute. I think we've lost one student here that just very puzzled. You with me? All right. Oxidation is loss. This is what we call the half equation. It's the half equation for oxidation. So in this equation here, when calcium bullied the magnesium, calcium lost its electrons. Calcium became stable. Calcium won. All right, calcium became the stable metal. Right, in this one then, we've got magnesium. Magnesium 2 plus is turning back into magnesium metal. To do that, to go from positive to a metal, you need to gain 2 electrons. I'm telling you now, it balances again. We've got 2 pluses and 2 minuses, they're all going to cancel out. So the story of magnesium is reduction. So reduction is gain of electrons. You will see the electrons on this left-hand side. Something is gaining electrons. Just read it really carefully. Mg2 plus is gaining 2 electrons to become magnesium metal. Do you remember the metal with its not full outer shell is now reactive again? So the more reactive metal actually becomes stable, it loses its electrons. The less reactive metal has to gain the electrons. This is not a story about the football. This is not a story about the Cl minus. That's just a spectator. This is a story about the more reactive metal will lose its electrons. The less reactive metal will have to just make do and gain some electrons. So this is my first example. The rest of the lesson is going to take shape like this. I'm going to give you probably, I think, 3 more worked examples where you gradually get a bit more independence. And then there is a worksheet to go through. All right, where it's just about practice. So the aim of today then, I've reminded you what an ionic equation is. I like ionic equations because they get rid of any spectator ions, so you can really see what's going on. Once we've got an ionic equation, we can write these little curly arrows to help us tell the half stories, the half equations. And we can turn these into half equations. Half equations are balanced with electrons. All right. Let's do a few more examples. They're going to get a little bit more challenging as to like, whoa, knock the camera over. Next, all right then. So I'm going to write an ionic equation first. This is the story of, now I need to get the reactivity right. Sodium's a reactive metal, right? So we've got sodium. I'll write a full equation first. NaCl plus, sodium's more reactive than lithium, right? Lithium. No, but I'll keep getting it wrong. Potassium. Right. Sodium chloride plus potassium. Oh, I'm so bad at chemistry. This is going to make potassium chloride plus sodium. I've written it round like this, okay. Little year 7, sodium chloride with the football. Potassium turns up, big bully. Potassium ends up with the football. More reactive metal ends up with the football and makes the less reactive metal. Can you now please get rid of the spectator ions, get rid of the footballs? All right, the football is a Cl minus. Just write an ionic equation. So get rid of the footballs, that's a Cl, that's a Cl. But I know they're actually Cl minuses, so that leaves an Na plus. This is a K, this is a K plus, and this is an Na. All right, let's find out, let's do a couple of little arrows now to find the stories. They're in a slightly different order. Sodium plus becomes Na, and in this story, K becomes K plus. All right, just finding those stories. All right. The more reactive metal was potassium. Potassium ends up with its full outer shell. The sodium has to just turn back into the metal. Right, two half equations then. You have two arrows if you like, because you know you're in two half equations, because two halves make a whole. All right, I've got the story of K becoming K plus and Na plus becoming Na. I would like you now to balance these half equations using electrons. So decide on this one, what side you're going to put electrons or electron on, and on this side, where you're going to put it as well, please. If you could just do that. Raise your hand if you've done that already. Okay, quite a few of you. All right, so potassium becomes K plus. That means that potassium has lost an electron, so we put that lost electron over there. A potassium could become a potassium ion, and there's its electron that it's dropped. And this one, Na plus an electron, I'll squeeze it in there. All right. Can you now write down which one is oxidation and which one is reduction, please? This one is obviously gain, so that must be reduction. Reduction is gain of electrons, and this must be oxidation. All right. Blah, blah, blah. Valid. Oxidation. Does say oxidation. All right. The more reactive metal is oxidized. Fairly straightforward. Next. Aluminium. Right, now I've got to get this right. Aluminium's going to be auxiliary. Right. Aluminium. Al. I'll do aluminium chloride. Chloride's always the football in these. It could be a bromide, it could be a whatever, it doesn't matter. Aluminium chloride. Aluminium is more reactive than... I'll go with zinc. It is more reactive than zinc. I think it is. Thank you. Thank you. One person laughed. I think it's like a nervous laugh more than anything. Like, yeah. Oh, I've done it wrong again. How did it? Ah! Oh, it's just so bad. It's just fundamentally like the totally wrong way round. The more reactive metal is the bully. Oh, I hope nobody who actually employs me is watching this video. Right, aluminium plus zinc chloride. Oh, I need more sleep. Thank you though. It just bodes well. Do A-level chemistry, please. Everybody in this room, you'll be really good at it because you're just very good. AlCl3. Now I'm going to tell you that because it has to. Right, plus zinc. The formulae are right, but the question in the room is, this idea of it's not balancing. Aluminium's in group 3, so it likes to have 3 footballs. All right, 3 minuses. So we need to balance this first. Can you firstly balance this equation to make the chlorines balance? So balance the chlorines. This will take a little bit of work first. I would balance your chlorines first. Okay, 3 chlorines on this side, 2 chlorines on this side. So I'm going to put a big number 2 in front of there. And a big number 3 in front of there. That balances my chlorines. And now I've got an aluminium problem. 2 aluminiums, 2 Als, 3 zincs, 3 Zns. All right. So on the surface of things, already it's a more challenging one because there's two aluminium bullies. There's bullying story. There's 3 year sevens and they've got 2 footballs between them. 2 aluminium bullies say, give me your footballs, and it all works out fine. It doesn't really matter, just balance it. What we're going to do now is we're going to get rid of the chlorides, which are the footballs. All right. So the story becomes 2 aluminiums. Where are we? We're really reactive. Meets 3 zinc ions. These are an ionic compound. You might be able to tell that the zincs were Zn2 pluses from underneath there. Well done if you did. Meet 3 Zn2 pluses. You would be given this in the exam. All right? This is what you'd be given in the exam. This becomes 2 aluminiums with a charge on them. Look how many chlorides they had. 3 pluses. Plus 3 zincs all crying their eyes out. We lost our football. Alright. So, there's a lot going on here. And there's lots of levels to this where you might be feeling a little bit uncertain. You still might not be sure where I'm getting these formulas from. You might not be sure where the ions are getting their charges from, but it's to do with the groups that they're in. What I want, the main focus for today is, if I gave you this, which is an ionic equation, with spectators removed, can we write half equations? That's the main focus for today. So let's find aluminium, and its story is 2 aluminiums become 2 Al3 pluses. And the story of the zinc is 3 zinc 2 pluses becomes 3 Zns. Now, at this point, we can actually get rid of the big numbers. I'm not too bothered. The story is really aluminiums became Al3 pluses. I know there were 2 of them, but the story is how does aluminium become Al3 plus? And the other story is how does zinc 2 plus become Zn? And this is the bit I've just got to reiterate with you. This is what you would see in the GCSE exam. All of this is trying to actually teach you A-level chemistry. This is the bit you would see in the GCSE exam. And they could give you this, and they would say underneath, they would go, aluminium becomes Al3 plus. Complete this half equation, or balance this half equation. That's all they would ask you to do. On this bottom one, it would be, complete this half equation, or balance this half equation. That's all I want you to do. Put some electrons on here, and balance these half equations, please. How does aluminium become aluminium 3 plus? What does it have to do? Anyone want to tell me that? How does an aluminium become 3 plus? How does it get 3 positives here? It loses 3 electrons, so we put them on this side. Aluminium becomes aluminium 3 plus by losing 3 electrons. It's got a full outer shell now. How does zinc 2 plus become zinc? Gaining 2 electrons. I'm just going to put them on the outside there because I didn't leave space. Alright, zinc gains 2 electrons. Oxidation is loss, reduction is gain. Last one. So the only difference with that was 3 plus and 2 plus. There was some tricky balancing up above. Right, see if I can actually get one right. This is the hardest thing I've ever done. Right. Why am I so thick on this? So poor. Right, potassium, a reactive metal. I'm going to put a plus in there before I try and write anything next to it. That will save me. Potassium is going to bully some calcium. I'm going to make it calcium bromide. Ooh, it's a different size football. Don't worry about it. Just a football. Basketball. Nice. Like that looks. Very good. Right. And then you're going to go. KBr plus calcium. Let's have a look at the science. More reactive metal, potassium, gets the football. Gets the negative ion. But really, the bromide is just a distraction. It's not about the football, it's about electrons. I'm going to balance this quickly. Br2, I'm going to need 2 of them. That balances my bromides. Now I've got 2Ks, 2K. Next job, please. Can you all write the ionic equation? Get rid of the bromides, Br minuses. Okay. They're all busy doing this. Right, get rid of them. Each of them is a bromide, Br minus, Br minus. That means the calcium is calcium 2 plus, like you would expect, because it's in group 2. 2K, so get rid of the bromides there. That would make 2K pluses, which you would expect, because potassium's in group 1. And then you're going to make a calcium. It should all balance, by the way. You should have 2Ks and 2K pluses. You should have Ca2 plus and Ca. So really what we're looking at is potassium becomes potassium plus, calcium 2 plus becomes calcium. You see like an opposite thing. Something's gaining electrons, something's losing electrons. That's why at A level we call it redox, reduction and oxidation. You can't have something losing it without something else gaining. All right, so full equation, ionic, we've got rid of spectators, and now we're doing half equations. All right, going to write 2 arrows for the half equations, if you can just crack on with this, please. Potassium becomes potassium plus. Calcium 2 plus becomes calcium. In an exam, they'd ask you to balance these half equations. 2 plus. Easy peasy, lemon squeezy. That's still a phrase. Good. Oh, we're not ready for that yet. Not ready for the sheet. No, it's got negative ions on it, you see. Got some negative ions on it as well. Right. So, if I was to take a pause there, let's go back to our front page just so I can see where we're at. I have told you today, well, focus, half equations tell the story of a reactant in terms of its electrons. And I've said that oxidation is when something loses electrons, reduction is when something gains electrons. I hope you've got the idea from what I've said that displacement reactions are an example of these. But really listen carefully, not every chemical reaction you can do this with. Alright? You can't, some chemical reactions out there don't involve movement of electrons. I'll try and show you one in a bit, maybe I'll show you one in a bit, but quite a few of them don't. Neutralization reactions don't actually. So what we've done so far is I've said, right, let's look at some of these oil rig reactions, these redox reactions in terms of displacement, because this is on the GCSE spec. It says on your specification, GCSE students need to know that displacement reactions of metals involve oxidation and reduction. It then says on your specification, GCSE students need to be able to balance half equations for displacement reactions. So typically in a GCSE, they will give you something like this, which is an ionic equation, and they could ask you to write half equations from it. So what we've seen is, to write half equations, you use 2 arrows because there are 2 halves that make a whole. You tell the story of 1 electron gaining electrons, so we put the electrons over here, and 1 electron losing electrons, we put them over there. The follow-up question for this, they would say in an exam, is this reduction or oxidation? And then all you go is, oxidation is loss, reduction is gain, this is gaining electrons. It is reduction because it is gaining electrons, that's all we do. Okay, time-wise, 34 minutes. Last bit. Going to show you another chemical reaction. This is also a redox reaction. So this is looking forward. Other oxidation, reduction reactions. All right. Going to write a sort of a classic. This is not displacement anymore. I'm going to write this sort of classic reaction of sodium. Sodium plus chlorine. Missed an L out there. Makes sodium chloride. We're not out of space on my page. That does say sodium chloride. Let's have a look to see if this is a redox reaction, if things are losing and gaining electrons. Symbol for sodium, Na. Symbol for chlorine, Cl2, well done. Sodium chloride, sodium's group 1, chlorine's group 7. Sodium forms Na pluses, chloride is Cl minuses, so it's just NaCl. Can you now balance that equation, please? 2 Cls, 2 in front of there, 2 NAs, 2 in front of there. This is hopefully going to be quite useful for you with your year 10 mocks coming up quite soon. This is the story of an alkali metal, sodium, symbol 2, electron configuration 2881, meeting chlorine, which likes to go around in pairs, electron configuration 287. And it's forming an ionic compound, MC buckle, high melting points, and all of this. My question to you is, firstly, are there any spectator ions? Is there anything that is the same on both sides? No, there is not. There is sodium, metal, that's not an ion, that's just salpidal, that's just sodium metal. This is chlorine, there are no ions on this side. There are some ions on this side. Sodium chloride is Na plus and Cl minus. But there is not a spectator ion, there is nothing I can cross out from both sides. Sodium meets chlorine and becomes sodium chloride. But what I can tell from this is my sodium, Na, has become Na plus, part of an ionic compound. My sodium has become Na plus in this reaction. And my chlorine, my Cl2, has split up from its neighbour like this. It's split apart. It's split apart from being Cl2, and it's ended up over here as Cl minus. So there is definitely some electrons being passed around here. My sodiums have become Na pluses, they've lost electrons. My chlorine seems to have become chlorides, they've gained electrons. This is oil rig. Alright, so let's write a couple of equations, half equations, sorry, to talk about these stories. In this story, sodium, Na, ends up in sodium chloride, an ionic compound, it becomes Na plus. I think you should be able to balance that half equation. If you can do that one first, please, before we move on. How does a sodium become a sodium plus? Does that by losing an electron, so we put that over there. This was sodium 281, sorry, I put too many 8s in there before. And this is sodium 28 plus, and it lost an electron. That's all that means. What sodium does when it reacts, it loses electrons. How it reacts. The story of chlorine is slightly more complicated because what we've got on the start is Cl2, chlorine gas. And at the end, it becomes 2 Cl minuses. There's chlorine gas, Cl2, going around in pairs like this, chlorine gas. And it becomes Cl minus. Each one of those becomes a Cl minus. If you want a little picture of it, there's chlorine gas, and at the end it becomes Cl minus, Cl minus. How does that work in terms of electrons? Where am I going to put electrons and how many are involved? How does a Cl2 become 2 Cl minus? Tell your neighbour, please. Any suggestions? Where might I put some electrons? Yes?
Would it be 2e minus?
It would, yeah. For a chlorine, what's going to happen is this Cl2 is going to come here. It's going to split apart, and each of these is going to gain an electron. You can think about it like that, or you can go, I've got 2 minuses on this side, so I need 2 minuses on this side. It's an easier way to think about it as well. 2e minus. This is a story of chlorine coming in a pair, picking up an electron each, and then being perfectly happy with their new full outer shell. Can you tell me which one of these is oxidation, which one is reduction, please? Loss of electrons. Oxidation is loss. Oxidation is loss oil. Reduction is gain. Right. This is more of an intro to where we might go, where we are going to go later on when we do something called electrolysis. I just wanted to show you another reaction that wasn't displacement, to highlight the fact that if an element changes from being an atom into being an ion, it must have lost electrons. And if something has lost electrons, the other chemical must have gained electrons. Which is why in chemistry, in later on, we call them redox reactions, because you can't have reduction without oxidation. So that's why half equations always come in pairs. So, what I'm going to do now, there's only sort of 5 minutes left of this lesson, so you didn't expect this if you were on DV, did you? You have to watch this at home. I hope you had a nice camping trip. What we're going to be looking at is we're going to be looking at some of these little sheets here where we're going to add and take away electrons. We're going to balance some half equations. So the examples I've been doing in class have been very sort of contextual, trying to build it up from scratch. Ultimately, all you need to be able to do at GCSE is if you're given a question that says balance this half equation, you've got to put the electrons on the correct side. That's it. All of this is a bit more A-level to try and get you thinking. I'm very aware some of you in this room will be a little bit, you'll have uncertainties all the way through. Trust the process with this. We've got another year with me doing lots and lots of these, dropping them in every now and again. So, what have we learned so far today? We have learned there are things called half equations, which tell the story of an electron, tell the story of an element in terms of its electrons, and we can balance these half equations by either putting electrons on the right-hand side or on the left-hand side. This is loss of electrons, this is gain of electrons. DV people, you can come and get one of these sheets when you come back, but it's just practice now. Good. Bye. Everyone want to say bye? Very enthusiastic. See, they were here. I can't show pictures of them because that'll be something like, what's that called? Safeguarded. Safeguarded. But they're all here.